LeChatlier's principle talks about what happens when we're not at equilibrium, especially if I was at equilibrium and then something disturbed it. What's going to happen? All right, so once a reaction is at equilibrium, the concentration of all the products and reactants are going to remain the same. But if something changes with the conditions and disturbs it, the equilibrium will be disturbed. Once it's no longer at that ratio, something happens, then the reaction will proceed in such a way as to restore equilibrium. So the new equilibrium concentrations are going to be different from the original equilibrium concentrations. However, the equilibrium constant will be the same unless there's a change in temperature. So the K is not changing unless K can change with temperature, but the K value isn't changing. But since the individual numbers are different, like reestablishes thing. So LeChatlier's principle says, if a system at equilibrium is disturbed, the position of equilibrium will shift to minimize the disturbance. Let's work through 3 different ways I can disturb a reaction at equilibrium and what LeChatlier actually means. So again, I have 3 different kinds of disturbances. One, I can change the concentration of a reactant or product. Actually, I'd say there's four disturbances. I can change the concentration of a reactant or product by adding more to the reaction mixture to increase it, or, and this is kind of tricky, the way it would decrease, I can't get there with a pair of tweezers and pull substances out of a system at equilibrium. But I can add in another substance that reacts with one of the substances in there, and thus, because it reacts it takes it out of equilibrium. So that's how sometimes the problem will just say the concentration decreases by this much, but other times it will just talk about a third substance being added that reacts with something and pulls it away and decreases its concentration. So changing concentration of a reactant or product by increasing it or decreasing it. I can also change the volume of a gaseous mixture, which changes the pressure or changes the molarity, right? So I'm changing the volume. So we can either think of that, you could do it in terms of Kc or Kp, doesn't matter. But so changing the volume or the pressure. And then the third one is changing the temperature of a reaction mixture, because the K is related to the temperature. So K remains constant unless the temperature changes. So it's not about K, it's about Q changing, which means it has to reestablish equilibrium by becoming equal to K. So we're changing, when we disturb it, we now move into Q, talking about Q, and we can evaluate it. So if I disturb the equilibrium by changing the concentration or the partial pressures of a substance, increasing the concentration or partial pressure of a reactant is going to decrease Q, and thus the reaction is going to shift to make more product, shift right. If I decrease the reactant, it increases Q, and so it will shift to the left. So it's going to go in the reverse reaction to get back to equilibrium. If I think about in terms of the products, if I increase the concentration or partial pressure of one of the products, that's going to increase Q. Because Q is now higher than K, it's going to shift to make more reactant, so it's going to shift left. If I decrease the concentration of a product or its partial pressure, it decreases Q, so then it's going to go in the forward reaction or shift right to make more product and reestablish equilibrium. So there's really only 4 things that can happen when I change the concentration. And it depends on, am I increasing it or decreasing it? And it depends on, is it a reactant or a product? And we can memorize it. There's a couple ways you can approximate these, but one way is you just memorize it. You can memorize it. You can calculate Q, the effects on Q, and then use your Q versus K rules, or just memorize them. Okay, the other kind of change I can have is I can disturb the equilibrium by changing the volume. This is only going to be a factor when we have gas products or gas reactants, when I have gas substances involved in the reaction. If the volume of the container of a gaseous reaction is changed, it changes the partial pressure of all the gas substances in the mixture. So the reaction will work to restore the change in partial pressure by shifting to the side that has more or less moles of gas substances, depending on what's going on. If I increase the volume, that's going to shift the reaction to the side that has more moles of gas. I want to reestablish it, so it's going to, if I calculate Kp and Qp, so increasing the volume, it shifts to the side that has more moles of gas. It's no longer reactant or product. I have to see which side has more moles of gas. Again, the moles of gas would be the sum of the coefficients of gases on each side of the equation. If I decrease the volume, it's going to shift the reaction to the side that has fewer moles of gas. If I add an inert gas, it changes the overall pressure, but it doesn't change the partial pressure or the concentration of substance. Therefore, it has no effect on the equilibrium. So that one's a little bit of a trick. Adding an inert gas is not going to have any effect. It does change them, but because it changes them all to the same amount, it doesn't have any effect. If both sides of the reaction have the same number of moles of gas, like I have 1 mole of this plus 1 mole of that gas makes 2 moles of this product gas, and they're both 2 moles on each side, then changing the volume disturbs both sides equally, therefore has no effect on the equilibrium. So it only is going to be disturbed when there's a difference in the number of moles of gas substances on the reactant and the product side. The third thing I can do is I can change the temperature. Now the problem is how the temperature affects K, because it changes K, depends on whether it's endothermic or exothermic. So we go back, recall that the equilibrium constant changes with temperature, and this disturbance is definitely the most complicated of them all. Change in the temperature changes the K. It doesn't change the Q, it changes the K. But I still end up in a situation where K and Q are no longer the same. But if I can, so one of the things that's tricks is I can think about heat as being a reactant or a product. In an exothermic reactant, I can think of the heat as being like a product of it. If I increase the temperature, I have more heat on the product side. That's going to cause a shift towards reactants. Whereas if I decrease the temperature, it's going to cause a shift towards the products. In an endothermic reaction, I can think about heat as being a substance on the reactant side. And again, remember, if I increase the temperature, I want to reduce that stress by going to the side that doesn't have heat. So that's going to cause a shift towards the products. If I decrease the temperature in an endothermic reaction, it's going to cause a shift towards reactants. Again, notice that we basically have 4 possible situations for what can happen when I change the concentration, and 4 possible situations that can happen when I change the temperature. In concentration, it depends on, is it a reactant or product? Am I increasing or decreasing it? In terms of temperature, is the reaction exothermic or endothermic? And am I increasing or decreasing the temperature? Remember too, when we look at endothermic and exothermic, I could be told directly that it's endothermic or exothermic. I also could be giving you a delta H for the reaction, the enthalpy of the reaction. Remember, negative enthalpies mean it's exothermic, positive enthalpies means it's endothermic. So sometimes the information is given to you in a subtle way. Another method that is popular and it works to get the answer, it doesn't explain things. It doesn't talk about Q and K and what's happening and thinking about the why, but it will get you the right result. It's called the seesaw method. And I'm visually seeing which side of the reaction is disturbed, so I can consider like the reaction itself is like a seesaw with a pivot at the point where the arrow is. If a concentration or partial pressure is increased, I can draw an arrow pushing up on that seesaw underneath whatever that substance is. So it would tilt the seesaw, and I can think about which direction, if I put a ball on it, which direction would it roll? Would it roll towards reactants or would it roll towards product side? I can also add heat into the reaction if it's a temperature thing, endothermic, exothermic. I think about whether heat would be considered a product or reactant, and I can consider it a substance, and it will work for that. If the volume is decreased, since it increases the partial pressure of all the gases, I need to draw a number of arrows based off of how many moles of that gas. I'm only going to write the gas substances, but I would draw the coefficient number of arrows up under each gas substance. Now, if the concentration or the partial pressure is decreased or the volume is increased, I can draw down arrows on top of the seesaw and think about what it would do. So I'm considering the arrows as pushing on the seesaw up or down, which way are they stressing the system, and determine which way the seesaw would tilt. The reaction shifts towards the lower seesaw side. So let me show you what this looks like. So in this example, 2N2, 2NO plus H2 gas makes N2O and H2O gas. And I have a delta H of negative 36, which tells me since it's negative that it's exothermic. Okay, case 1, I'm adding NO. Since NO, this would be increasing the concentration. Since NO is added, it's increasing the concentration of NO. So I put my original line with the pivot at the arrow. If I increase NO, I put an up arrow underneath. That's going to tilt this up and it's going to shift to the right. If I remove hydrogen, again, how would I remove hydrogen? I might add something that reacts with it, or it could just say I remove it. I'm going to use the down arrow. The down arrow is going to go on top of the seesaw, pushing it down on the left side. Therefore, it's going to roll to the left side. So this would be shifting left. If N2O is added, since that's a product and I'm increasing it, I'm going to put an up arrow underneath. Again, I can think about what this is happening and what's happening to Q that's the correct way to think of it in terms of concepts. But to get the answer, if I increase on the right side of the pivot, it's going to shift to the left. If the volume is compressed, so volume is decreasing, that's going to be increasing the partial pressure for everything. I am going to put arrows underneath for the gas. I'm going to put the number of arrows I put would be equal to the coefficient. So 2 up arrows for NO, 1 up arrow for H2, 1 up arrow for N2O, and 1 up arrow for H2O. Since I have 3 pushing up on this side and only 2 pushing up on this side, the left side is going to be pushed higher because there's more arrows, and thus it's going to shift to the right. If the system is cooled, that's a temperature change. Now I want to consider the fact that this is exothermic. Since it's exothermic, I can think of heat as a product. Since it's being cooled, I'm decreasing the heat. So I will put a down arrow on the heat, which is going to tilt it towards the right. So the temperature is going to disturb the product side, shift right to make more heat. So I can use this as a way to get the answer and maybe a little bit less. However, you should be able to construct arguments about what's happening to Q or what's happening to K, and thus which one is bigger or smaller in which direction the reaction proceeds.